In this video series, I'm talking about interaction. So let's actually look at an example of interaction using actual data and doing some analysis in an R notebook. So I'm going to use the IQ and physical measurements data. This data set has 4 variables in it. It has IQ scores from the Wechsler Adult Intelligence Scale. It has brain size as a potential explanatory variable. Now, the brain size here is based on the count obtained from MRI scans given as count divided by 10,000, but I don't know what that means. We can just talk about it in terms of a brain size unit because I don't know if the count is pixels on the MRI divided by 10,000. I don't know what that is. Then we have 2 additional explanatory variables, height, which is given in inches, and weight, which is given in pounds. So let's take a look at this R notebook that I've constructed. And we're going to look at the relation of IQ to brain and body size. So first I'm going to read in the data. And let's take a look. Here is the little spreadsheet version of the variables. IQ in the first column, brain, height, and weight. Since the response variable is IQ, and we have 3 potential explanatory variables, in order to do linear regression, including multiple linear regression, I need a linear relationship of these explanatory variables with the response variable. So let's see if that's feasible. I'm going to create scatter plots for each explanatory variable with the response. So first we're going to look at brain and IQ, brain size and IQ. And I don't see anything that looks real curvilinear here. I could imagine a line kind of going, not a lot of steepness to it, but a line kind of going through these data. There's no obvious curvilinearity to me here. Let's now look at IQ and its relation to height. Again, that actually looks like a line would fit quite nicely through these points. And the higher we go, the higher the IQ. Taller people having higher IQs here according to this. And then let's look at weight. And similarly, heavier people, more weight, higher IQ. And again, maybe a touch of a little bit of curvilinear here. It kind of comes up and then kind of flattens out, sweeps over, but not too far off from being linear. So I'm certainly not going to discount this as a possible variable in my equation based upon that slight curvilinearity, although a curvilinear model might do slightly better for this particular variable. All right, let's look at correlations among these. So the first row will give us the correlations of the explanatory variables with the response, and I see that brain size is the largest of these correlations at 0.38. Weight is just about 0. And height there is a correlation, but a fairly weak one of negative 0.09. The largest correlation that I see is among weight and height. That is, the taller you are, the heavier you are, which makes sense. This is 0.70. So that's a pretty strong correlation among height and weight. I'm going to keep that in mind when I create my model because much of the variation in height overlaps with the variation in weight. And so much of this will be explaining the same thing in terms of variation in IQ for these 2 variables of height and weight. I also see that height and brain size has a fairly strong correlation, at least a moderate correlation of 0.59. Let's start by looking at the full model here. When I look at the full model, what I notice right away is that weight isn't contributing anything. Height and brain size, those are both quite stable in this model. I also notice that I'm accounting for 30% about 30% of the variation in IQs can be explained by or is associated with variation in brain size, height, and weight, although as I already pointed out, weight is really not doing much of anything here. In fact, look at this estimate. This estimate is 0.0006. So that's about as close to zero as you will ever see in a regression coefficient. Now, having said that, I also remember that height and weight had a lot of overlap. So I suspect if I take out weight, height will still account for a lot of the variation and vice versa. So given the strong correlation of height and weight, let's try a model that only includes height and another one that only includes weight. First, here's a model with brain size and height. And when I look at this model, no surprise, brain size and height are both very stable coefficients. Notice that I'm still explaining about 30% of the variation. I lost basically nothing by eliminating weight. But let's do it the other way around just to convince ourselves that weight is not valuable here. And indeed, I see that even though height is no longer in the equation, weight is not really stable. Not too bad, but a p-statistic of 0.15. But I also notice that I dropped all the way down to 0.19, 19% of the variation accounted for. So I am thoroughly convinced that I can take weight out of the equation, have a more parsimonious equation that's just as good as if I had had weight in there with just brain size and height. So we're going to stick with this model here, brain size and height. We're going to account for almost 30% of the variation in IQ with those two variables. But now I want to understand it better because I want to know what is the effect. What is the effect of brain size on IQ? What is the effect of height on IQ? Let's go ahead and do the following. Let's look at the relationship of brain size and IQ for two different heights. I've chosen, rather arbitrarily, although I would want to make sure that the numbers I choose are within the range of my data. I've chosen someone who's 65 inches and someone who's 75. And let me go ahead and look at what the range is in the data. If you look over here in the console, I'm going to type in that I want to know what the minimum is for height in the data and what the maximum is for height in the data. Okay, 62 and 77. So I'm well within range. If I were to get out of range, it wouldn't make a lot of sense because I would be extrapolating beyond the range of the data that I have in hand when I made this model. This model was made based upon using individuals from 62 to 77. Now, before I draw these pictures, let's also look overall what the effect was. Go back and interpret these effects. So for brain, for every unit of increase in brain size, and remember I said at the beginning I don't really understand what those units are, but whatever they are, for every 1 unit increase in brain size, we have 2 points addition to IQ. Conversely, notice, and that is on average, and that is controlling for height. Always got to say those things. So on average, an increase in 2 IQ points after controlling for height. Conversely, after controlling for brain size, for every unit increase in height, that would be 1 inch, for every 1 inch, we come down about 2.7 IQ points, about 2.7 down. Now you might say, wait a minute. Don't you recall that scatter plot? Yes, I do recall it. Here it is. That scatter plot shows a positive correlation. So why is it that we're now seeing down here in this model that we've chosen, why are we getting a negative coefficient when we have a positive correlation? That's because that scatter plot is not showing what we're really looking at down here, and that is we're looking at the residual after accounting for brain size correlated with IQ. We're looking at height after we've already taken out brain size, so that you can think of it as a residual, that brain size has been taken out of height. And when that's happened, then all of a sudden we find this negative relationship. And it's a pretty stable one. Okay, so now let's go back and look at these pictures. First, let me show you what I've done here to get these pictures. This is the model that we chose, BH for brain height, the brain height model. The first coefficient, remember, is going to be the intercept. So if I were to actually look at each of the coefficients here for the brain height model, and you see that you can see them right here on this line, the first coefficient is 111.28, which we also could see back up here, 111.28 in this model we chose, okay? But it's also the first in a vector of coefficients. A vector just means a list. The first in a list of coefficients. And then 2.06 would be for brain, and then over here I see negative 2.73. So what I'm doing is taking those coefficients one at a time and building my model. Intercept plus the coefficient for brain times whatever the brain variable says at the time. That is, I'm leaving the brain variable in there, plus the coefficient for height. But now instead of looking at all the possible heights, I'm just looking at 65. I'm holding it constant. And think about what we talk about when we talk about coefficients and regression equations. It's after holding the other variables constant. So I'm holding this constant at 65. Down here, I've repeated it. I've done the exact same thing, but this time holding it constant at 75. So this will give me a model holding the height constant 65, and this one will, or give me predictions rather, holding it at 65, and this one will give me predictions. That's why I called them Y hat, holding it at 75. Then what I'm going to do is I'm going to plot. So this is going to plot brain on the x-axis, my prediction, brain on the y-axis, that's my response variable. Brain on the x-axis, so response variable is IQ. Brain on the x-axis, my predicted IQ for 65 inches on the y-axis. I'm going to put in a line, and then I'm going to label the axes and do a little bit of limiting of the range to make a nicer plot. Then I'm going to put in just a line on top of that plot for IQs that I predict for 75. So keep in mind that the Y hat 65 is a predicted IQ for someone who's 65 inches, and this for 75 inches with varying brain sizes. All right, here we go. And there's my picture. So this is the relationship here of brain size to IQ. As brain size increases, so does IQ. The same is true for 75, and in fact, they're at the same rate. Why? I had no other choice but to leave them at the same rate, because my model has the exact same coefficient, regardless of whether you're at 65 or 75. It has the exact same coefficients in, so the slope's going to be the same. So these are necessarily going to be parallel lines. What's this gap tell me? This gap tells me that 65 inches has higher IQ than 75 inches if in fact the brain size is constant. If the brain size is constant. So what likely is happening, this is not saying that taller people are less intelligent. What it's kind of telling us is that, not kind of, it is telling us that it's brain size relative to height that's important. So when you are taller, bigger bone structure, bigger head, bigger cranium, larger brain, you tend to have that larger brain. And so therefore, someone who has a larger brain at 75 inches could be the same intelligence as someone with a smaller one at 65 inches. So that gap you see is assuming that you're holding the brain size constant. And the fact is that typically when you get taller, the brain size increases. But holding the brain size constant, then we would have higher IQ for the 65 inches than the 75. All right, so I'm going to continue looking at this in the next video. What we have left to do is to look at a possible interaction, and we've not entered that yet, so we will do that in the next video.